Hello everyone, and welcome to this series on ordinary differential equations. In this video, we're going to introduce the main ideas that you definitely should understand before exploring or possibly revisiting the realm of differential equations, whether it be ordinary or partial, stochastic, fractional, or any type of differential equation. So if you're new to the realm of differential equations, a natural question to sort of begin this journey is to answer the question, what exactly is a differential equation? So a differential equation is an equation that contains the derivative or higher order derivatives, typically natural order derivatives like first, second, third, fourth, fifth, 76th derivative of a function, curve, or relation, i.e. it need not be a univariate function. It could, for example, be a circle, it could be an ellipse, i.e. it doesn't have to pass the vertical line test. So it can be an arbitrary relation function or geometric curve. Anything will be okay, as long as it's an equation that contains the derivative of some relation, the rest will just do. So let's just give a basic example that you've probably already seen, especially if you've already explored, say, single variable calculus. So let's assume we have the derivative of some function y, and let's assume that this represents the derivative of y with respect to x. And let's assume that this is equal to x squared minus cosine of x plus 5. So this is a differential equation because it has the derivative of some unknown function y in this equation. And the question that we want to answer when we see something like this is, what exactly is this relation y equal to? And in particular, if the derivative is a function of x, then the original relation should also be a function of x as well. So if you took single variable calculus, you probably know that there are actually infinitely many solutions to this particular differential equation that all vary by some constant c. Because notice that we can actually just take the integral of both sides of this equation with respect to x, because notice that this is the same as the differential of y is equal to x squared minus cosine x plus 5 times the differential of x, and then we can integrate both sides, and we just have y on the left-hand side, and then on the right-hand side we're just going to have 1/3 x cubed minus sine of x plus 5x plus some arbitrary constant. Let's call it c just for now. And that would be the general solution, what we say. So that's the general solution to this differential equation, which I'll just abbreviate by DE. Now, if you sort of draw a bunch of value of these curves for various values of z, you're going to get infinitely many looking curves. But sometimes we want a particular solution. So for example, let's assume that we have the differential equation y prime is equal to x squared minus cosine of x plus 5, and let's assume that we know an extra piece of information about that actual solution. Let's assume that when x is equal to 0, y is equal to 3. Some people will refer to this as an initial condition, and this whole entire statement as an initial value problem. Some people will abbreviate that as just as IVP. And then when we solve this initial value problem, you're not going to get a general solution, but more so a particular solution. And hopefully that particular solution is a unique one. So we already know that our general solution is y is equal to 1/3 x cubed minus sine x plus 5x plus c, and we want to know the value of c that satisfies this initial condition. So when x is equal to 0, what is the associated value of c that produces a y value of 3? So when y is equal to 3, the rest is going to be 0. So you have 0 cubed sine 0, 5 times 0 plus some unknown value c. Notice that this entire right-hand side except for the c is going to be equal to 0. So we have 3 is equal to c as our constant, and therefore y is equal to 1/3 x cubed minus sine x plus 5x plus 3. This is the solution to the initial value problem, and so that's one thing you can say, and it's also a particular solution to the general differential equation before I actually mandated a particular value that this relation passes through, right? So that's what a differential equation is, and at least a large class of differential equations that you can probably already solve, just as long as you know some basic integration methods. So let's start off with a nice introduction to differential equations. Let's assume so if someone proposes a solution to a differential equation, we should be able to verify if it is actually a solution, or we should be able to verify that it is not a solution. Now, we might not be able to know exactly where the solution came from, but we should be able to at least test whether the solution is feasible or not. So let's look at a couple basic examples. Let's assume that we have the differential equation x times the derivative of y is equal to 2y, and the proposed solution, so the proposal, is that the solution is y is equal to 5x squared. So somebody claims that this is a solution to the differential equation. Emphasis on the word a. It might not be the only solution, but you should be able to verify that it is a particular solution, right? Even if I were to put a constant cx squared there, that doesn't necessarily mean that that's all of the solutions either, even if it is more than one. So let us see if we can verify that 5x squared is or is not a solution to this particular differential equation. So if this is our particular claim, y is equal to 5x squared, then the derivative of y is just going to be equal to 10x via the power rule. So we know what y prime should be equal to. So if y prime is equal to 10x, then if we multiply y prime by x, then that's going to be x times 10x, which is just going to be equal to 10x squared. So that's what y prime should be equal to. So that's the left-hand side of this differential equation. Also, what is 2 times y? So now I'm focusing on the right-hand side. So 2 times y is going to be equal to 2 times 5x squared, which is equal to 10x squared. So that is the right-hand side of this differential equation there. So if this is truly a solution to that differential equation, then the left-hand side must be equal to the right-hand side for this particular function. So if you notice that both of these are equal to the same exact value for all values x, right? So we see that 1 is equal to 2 for all x in the set of real numbers, and hence any subset thereof, if you want to choose on a subset, solve this differential equation on a particular subset of that domain, that's perfectly okay. So that means y is equal to 5x squared is, in fact, a solution, possibly not the only solution, but it is a solution to the differential equation. So that's pretty nice. Now notice that this solution that I proposed was already solved for y, because we said, y is equal to 5x squared, i.e. this is already solved for y explicitly, i.e. y is equal to something with not y in it, right? Because notice that there's no y's on that right-hand side, just x and possibly some other constants too. So this is usually what we refer to, if this is solved in this particular form, as an explicit solution. Most of the time we can't always algebraically solve an equation, even though it is a solution to a differential equation. In that particular case, for example, this next one, let's assume that our differential equation y prime is equal to y squared all over xy minus x squared, and let's assume that the proposed solution is y is equal to e to the y over x. Notice that we have y's on both sides of this equation, but notice that this does not have any derivatives in it, so this still can be a solution to that differential equation, but it's an implicit solution, or possibly isn't a solution, right? We have to verify that, of course, right? So you don't always have to solve for y, because sometimes algebraically you can't. That's where special functions sort of enter the conversation. But you still should be able to verify that implicit solutions are actual solutions to this differential equation as well. So let's assume that we have the proposed solution y is equal to e to the y over x. And let us first find the derivative of this expression. So the derivative of y, and keep in mind this is the derivative of y with respect to x, is going to be equal to, so we can perform a chain rule on this expression, right, by taking the derivative with respect to x of both the left and the right hand side. So the derivative of e to the anything is going to be e to the anything times the derivative of that interior, so we can use a quotient rule. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So that's going to be what y prime is equal to. Now, you could stop there and say, okay, well, y prime is equal to that, so that's the left-hand side. You can plug in this value of y into this expression everywhere we see y and simplify that and hope that they sort of come out to the same exact thing. That's one approach. Or we can take this expression and try to algebraically manipulate this into the right-hand side. And sometimes you can see that they're very different from each other and there's no possible way to transform them. And both ways are perfectly valid, but you should use discretion on the problem you're working with to see which one is more appropriate. Okay, so what do I have here and how can I rewrite this expression? So one thing I can do is I can get rid of this fraction by multiplying both sides of this equation by x squared. That's going to get rid of that expression on the denominator. So now I'm going to have x squared y prime is equal to e to the y over x times xy prime minus y. And we're trying to show that y prime is equal to y squared over xy minus y squared. That's what our goal is. So we need to get our y prime to the same exact side. So that means we need to distribute this thing into this expression. And that's going to give us x squared times y prime is equal to xy prime e to the y over x minus y times e to the y over x. Now I can shift this term to the left-hand side and leave the right-hand side alone. And what is that going to give us? Let's see here. So when we do that, that's going to give us y prime times x squared minus x e to the y over x is equal to minus y e to the y over x, remaining on the right-hand side. Now, it's sometimes useful to keep in mind exactly what we're aiming for. We're trying to aim for y prime is equal to y squared over xy minus x squared. And notice that in our expression, we have an e to the y over x and e to the y over x appearing here, and we don't have that anywhere in the goal. So that's, of course, going to create a stumbling block eventually if you don't, fix that earlier on, but keep in mind our proposed solution was that y was equal to e to the y over x, and we can just use that as a substitution in this expression and see if that works out. So once we do that, we're going to have y prime times x squared minus x times y is equal to minus y times y, which is going to be equal to y squared. And then we can divide both sides by x squared minus xy, and that's going to give us y prime is equal to minus y squared all over x squared minus xy, which is a perfectly valid way to represent it, where you can multiply top and bottom by -1 and write that as y squared divided by xy minus x squared, and that is also an equivalent way of representing it. So keep in mind, our proposed solution was that y was equal to e to the y over x, and the equation that it was proposed to be a solution of was this exact equation here. Therefore, we have that this is an implicit solution to this differential equation, which is pretty nice, I think. So now that we know how to at least verify that a proposed solution is a solution or not of a differential equation, now I want to talk about a few different varieties of differential equations, and that's going to sort of partition our full discussion of differential equations into a bunch of little subunits, because each of them have their own flavors of solutions and sometimes difficulty on how to solve them as well. So the main partition of differential equations probably would be partitioning differential equations into either what we call ordinary differential equations and partial differential equations. There's also other classifications of differential equations such as stochastic and fractional differential equations, but we'll worry about them at a later time because you sort of need to treat them vastly different than both ordinary and partial. So these are just the two that I want to focus on, at least for now. So ordinary differential equations are where you just have one unknown function of one independent variable. So for example, y being a function of x. So for example, that would look like the derivative of some unknown function y plus some variable x is equal to sine of x. So in this particular case, y is assumed to be a function of x only. Whereas on the partial derivative side, you would have something like the partial derivative with respect to t of some function u plus the partial derivative with respect to x of some function u times the variable x is equal to just the variable x. And here I'm assuming that u is a function of both x, t, and potentially other variables that aren't appearing in this particular equation. So ordinary, our unknown function is just a function of a single variable, and partial differential equations are usually looking for a function of multiple variables, typically some spatial variables like x, y, z, and some temporal variable or variables such as time. Right, so that's the first classification thing that you definitely should know when it comes to differential equations. The second classification of differential equations is usually associated to the order of the differential equation. And the order is simply the highest derivative operator appearing in the equation. Appearing in the differential equation, and this goes for both ordinary and partial differential equations. So as an example, let's assume we have y double prime minus xy prime plus y is equal to y prime to the power of 3. So what is the highest order derivative that you see in this picture? The order in this case would be equal to 2, which is appearing right there. Please do not get mixed up with that 3. 3 is just an exponent because that's just y prime times y prime times y prime, which is not y to the third order. They're very different from each other. So it's just the highest order operator for the derivative that is appearing in this particular equation. As another example, let's assume we have y prime minus y plus y5 plus y7 y3 multiplied together is equal to y. So what would the order of this differential equation be? So that's a first order derivative operator, that's a 0th order operator, that's 5th order, that's 7th order, that's 3rd order, and that's 0th order as well. Therefore, the highest appearing here would be this operator here. Therefore, in this case, the order would be equal to 7. Keep in mind, just because we're multiplying them, the 7th derivative times the 3rd derivative is not the 10th derivative, right? Because that's the product of derivatives, not a derivative of products or anything of the sort. So that's how we classify the order of a differential equation, and in some sense, partial derivatives are harder to solve than ordinary differential equations, and the higher order differential equation you have, also the more difficult it is to solve as well. So the next classification I want to bring up is homogeneous differential equations versus inhomogeneous. Some people also call it non-homogeneous differential equations. So, and again here, inhomogeneous equations are typically going to be more difficult to solve than homogeneous differential equations. So let's give one example. So a homogeneous differential equation would be y double prime minus 2xy prime plus 5y is equal to 0. And I'll give you another example of a differential equation, y double prime minus 2xy prime plus 5y is equal to 7. What's the difference? Can you take a guess of which one is homogeneous and which one is inhomogeneous? The correct answer for the classification between these two is the first one is what we call homogeneous, And the last is what we call inhomogeneous, right? So in terms of the formal classification of homogeneous and inhomogeneous differential equations, every term in this expression, every non-zero term, so every non-zero term has our variable and the unknown function in it. Whereas here, this does not have x, this does not have y, it doesn't have x squared, doesn't have y to the third order, doesn't have anything like that. So in particular, it has no non-zero constant terms. That's the easiest way to go about classifying ordinary differential equations as either homogeneous or inhomogeneous. And as usual, as expected, inhomogeneous equations are going to be a little bit more difficult to solve. The next classification for differential equations that you definitely should know is linear versus nonlinear differential equations. Linear differential equations are actually quite easier to solve, even if they are a higher order, but nonlinear differential equations are a complete majestic beauty, but completely ugly and annoying to solve. It really depends. Some are nice, but usually they can get really, really difficult to deal with very, very quickly just with slight modifications. So let's see if you can pick up the difference between a linear versus nonlinear differential equation. So let's look at y double prime minus 5xy plus the square root of x is equal to 5, and the sine of y plus y prime squared plus y squared plus 5x is equal to 2. One of these is linear, the other is not. Can you take a guess of which one is the non-linear one? So the first equation would be the linear differential equation, and the second will be the non-linear differential equation. So one way to sort of formally define what is a linear differential equation, at least in the ordinary perspective, one thing you can do is you can replace y prime, y double prime, all the way down to the last order derivative, all with some variable. It doesn't really matter which variable you choose. You can call it whatever you want. Let's call it w, just for fun. And ask the question, is it an algebraic linear equation that you can solve with just basic algebra? So that's the question we would have. So if we look at this first equation, what exactly would we have when we replace all the derivatives, including the zeroth derivative with w? So that's going to give us, for our first example, w minus 5xw plus square root of x is equal to 5. So what I can do is I can factor out my w, so I'm going to have 1 minus 5x times w plus the square root of x is equal to 5. Can you solve this equation for w? So if you sort of look at the right-hand side, what you sort of have here is a y is equal to mw plus b equation, where w is my variable. So obviously you can shift that minus 5 to the left-hand side, it's still a constant b, so that would be a linear differential equation. But if we look at our second example, where we have, for example, the sine of w plus w squared plus 5x is equal to 2, obviously, that's not a linear equation, that is a quadratic equation, so that would be a quadratic differential equation, and the sine w doesn't really make anything nice at all. Although you could say, okay, well, if w is close to 0, this is approximately equal to w, but even then we still have this quadratic term that's going to cause us problems. So this would be a nonlinear differential equation because you cannot write it in a linear form if you replace all of your w's or all of your derivatives with some simple variable, say w. The next classification of differential equations that I want to introduce is a set of differential equations known as homogeneous differential equations or homogeneous symmetric differential equations. And the complementary of homogeneous symmetric differential equations would be homogeneous asymmetric differential equations, or some people also say homogeneous differential equations. So, what exactly is a homogeneous symmetric differential equation? So the first requirement is you write your differential equation in the form y prime is equal to fxy over gxy. So if it's a first order differential equation, that's at least what this definition is focused on. First you solve for your dy over dx term, and then you're going to have a function on top and a function on bottom. The next thing is you're going to replace x with cx, you're going to replace y with cy, and you're going to factor out your c, and hopefully you'll have c to the power of alpha 1 times the original function with no c's in it. If that is the case, we call alpha 1 the degree of homogeneity for the function f. You're also going to do the same exact thing for g. You're going to replace x with cx, y with cy. Hopefully you can factor out that c out of everything and write this equation in the form c to the power alpha over 2 times your original function, and that should be g with no c's in it. And alpha 2 would be the degree of homogeneity for the function g, right? And if you cannot represent these functions in this particular form, then we say that those are inhomogeneous symmetric differential equations, or actual inhomogeneous symmetric functions, and hence you won't be able to write this as a homogeneous symmetric differential equation in the first place. But let's assume that you can do this for both f and g. And lastly, let's assume that the degree of homogeneity for f and g are equal to each other. If this is the case, then the differential equation you have here is what we call a homogeneous symmetric differential equation. Now, this may seem a little bit complicated at first, but don't worry, there is a lot of beauty of why we go through defining these things in the first place. So we're not going to go through how to solve homogeneous symmetric differential equations, at least today, but you should be able to at least tell whether or not you have in your hands a homogeneous symmetric differential equation. Right, so let's look at an example. Let's assume that we have y prime is equal to x squared plus xy, or yx, divided by the square root of x squared plus y squared. Right, so since we've written this form into y prime is equal to something over something, what we're going to do is we're going to call this our function f of xy, and we're going to be calling this function our function g of xy. And let's assume that the variable x and y are both positive, for example. Right? They both can't be 0 because that's going to give you 0 in the bottom. So let's just make them both non-negative. So first off, are f and g homogeneous functions? If they are, then when we replace x with cx and y with cy, so we're going to get cx squared plus cy cx, we should be able to factor out some c's. And so in this case we have c squared xy, which is just c squared times x squared plus yx. And notice that the thing in parentheses is precisely the original function, so this is equal to c squared times fxy. So f has a degree of homogeneity, let's call it alpha sub f, of 2, right? And then we're going to do the same exact thing for g. So g of cx cy will be equal to the square root of c squared x squared when we square that term. And then we're going to have c squared y squared on that term. We're going to factor out our c squared, so we're going to have c squared times x squared plus y squared. The square root of c squared is going to be the absolute value of c, but c is positive, so it's just going to be equal to c times the square root of x squared plus y squared. That square root is the original function, so we just have c times gxy. So we have that g is also a homogeneous function, and in particular the degree of homogeneity for g is going to be equal to, so alpha subscript g, it's a strange looking g, alpha subscript g is going to be equal to 1. So once you find out that both are homogeneous functions, then you need to make sure that they have the same exact degree. But notice here I have a degree 2 and a degree 1. Therefore, this is not a homogeneous symmetric differential equation. Right? It's a first order differential equation, that's obvious. It's a nonlinear differential equation because we have y squared. And you can probably throw a couple other classifiers on this as well. But it's not a homogeneous symmetric differential equation. That much is obvious. The next classification of differential equations that I want to discuss is what we call separable and non-separable differential equations. As usual, non-separable equations are going to be typically more difficult to solve, generally speaking, than separable differential equations. And separable differential equations are actually usually very, very easy to solve, as long as you know basic integration techniques. So first off, let us define what we mean by a separable differential equation, and let's define this in terms of first order differential equation, and we'll extend this later once we are ready. So a differential equation is said to be separable if it can be written in the form y prime, which keep in mind is going to be dy dx, is equal to some function of x only divided by some function of y only, right? So dy over dx is equal to fx over gy. So dy over dx, fx over gy. So x only on top, y only on bottom, y differential on top, x differential on bottom. So they're on opposite sides of the fraction, I guess you could say. So if it can be written in this form, then we call that differential equation separable. Now let us introduce our first theorem, which is actually not too hard to prove. So if a first order differential equation is separable, then it can always be solved using basic integration. Provided y itself is differentiable. Right? So if it does indeed have a derivative and it has some nice expression, then you should be able to solve this separable differential equation using elementary methods. Right? So let's actually give this a proof since it's not quite difficult. So let us assume that dy dx can be written in the form f of x divided by g of y, where the top is a function of x only and the bottom is going to be a function of y only. Right? So also, since we're assuming that these functions are, say, integrable, then let's denote the derivative of some function, capital F. Let's assume that let's assume capital F is the antiderivative of f, and let's assume that the derivative of capital G is equal to little g, i.e. capital G is the antiderivative of little g. So if that is the case, then what do we have? So what I'm going to do is I'm going to rewrite this equation. So I'm going to write this as gy dy is equal to fx dx. So I'm multiplying both sides of this equation by gy dx. So once I have that, then I can integrate both sides of this equation, because notice that I have a real number and an infinitesimal. So when I integrate a infinitesimal times a real number, I should get a real number back again, since the integral and the infinitesimal sort of are compatible with each other. And the same thing can be said about the right-hand side. So we already know that capital G is the antiderivative of little g, so we can rewrite that as capital G y plus some arbitrary constant c1, I guess you could say, and the right-hand side would be capital F of x plus some arbitrary constant c2. Some people will just combine the c's on one side, either the left or the right. It doesn't really matter. So what we can do is we can define capital C to be equal to c2 minus c1, or you can just define that c to be arbitrary anyway. So what we have here is gy minus fx is equal to some arbitrary constant c. And notice that this is the general implicit solution to our separable ordinary differential equation. And that completes the proof. So if it's separable, we can always solve it. Sometimes these antiderivatives are sometimes a little annoying to find, but as long as g and f are integrable, then you should be able to find those functions capital F and capital G, at least theoretically. Let's work through a couple algebraic examples, since this actually gives us a large class of functions and differential equations that we can actually solve up front with knowing minimal theory about differential equations. So the first differential equation that I want to solve with just these basic elementary methods is going to be equal to sine y times y prime is equal to x squared. Let's first off classify what we're actually looking at here. So this is obviously a first order. So is it a homogeneous differential equation? It's definitely homogeneous. Let's see, is it linear or not? So it's obviously nonlinear. So it's a first order nonlinear because we have that sine y term, and that's a nonlinear term. So we have a first order homogeneous nonlinear ordinary differential equation, right? I'm not going to test the other classifications, but that's actually the basic ones that you always should start looking at. So if this equation is separable, because keep in mind we are working with a nonlinear differential equation, which in general can be very difficult to solve, but if it's separable, we can always find a solution, which is wonderful. Right? So let's see if we can write that in the appropriate form. So if we can get our y's on the left-hand side and our x's to the right-hand side, we're practically done. So what we have here is we have sine of y times differential of y divided by differential of x is equal to x squared. So what we have here is sine of y times dy is equal to x squared times dx. So we have our y's on the left, x's on the right, therefore separable, which should make you smile. So from here we can integrate both sides of this differential equation. So the antiderivative of sine of y is going to be equal to minus cosine of y. Let's put our constant on the right hand side just to make things clean. The antiderivative of x squared will be 1/3 x cubed, and let's throw our constant over here. Let's call it, for example, c1. Now I'm going to get rid of this minus sign here because I don't like this minus sign on my left-hand side. So I'm going to write this as cosine of y is equal to minus 1/3 x cubed plus some new constant c2, which is just going to be the opposite of constant c1. So this technically is our solution. It is the implicit solution, but we can actually solve this equation very, very simply because we should know the inverse of cosine. So if we invert the cosine function, as long as we have restricted that domain in an appropriate way, then we have the explicit solution as y is equal to the arc cosine. Let's call it, let's do c2 minus 1/3 x cubed. I think that's a nice way of writing it. So that would be our explicit solution to our original separable differential equation. So not too difficult. Let's do one more example just for fun. So example 2. Let's suppose we have x times the differential of y minus 1 plus y squared times the sine of x times the differential of x is all equal to 0. Okay, so notice I have a minus sign or a plus sign in the middle, so putting that on the right hand side is definitely going to be a reasonable first step. So we're going to have x times dy is equal to 1 plus y squared times the sine of x times dx. Now what I want to do is put all of my y stuff to the left hand side because that's where my differential y term is, and I also have my x term on the left hand side, so I'm going to move that to the right hand side. So my x's are going to cancel, my 1 plus y squareds are going to cancel, and that should put us in a very friendly form. So we're going to have dy divided by 1 plus y squared is equal to sine of x over x dx, right? Everything with y on the left, everything with x on the right-hand side. So therefore what we have is a separable differential equation, which should make you happy. So from here, what do we have? So we're going to be integrating both sides of this equation. So the antiderivative of 1 over 1 plus y squared, that's going to be equal to the arc tangent of y. The antiderivative of sine x over x is non-elementary, but we should know the name of it by now, maybe. That's the sine integral function. And let's put our constant on the right-hand side. Let's call it c, right? So that is our implicit solution. But we should know the inverse of the inverse tangent function. That would just be tangent. So that means our explicit solution will be equal to y is equal to the tangent of, or constant c, plus the sine integral function of x, right? And that is our solution to our original separable differential equation. So up to this point on this first video of differential equations, I've actually given you several different classifications of what differential equations can be in the forms that can take: linear, nonlinear, homogeneous, inhomogeneous, separable, non-separable, and so on. So as you can imagine, these differential equations can be very, 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 very difficult to solve. So a natural question is, well, what if you can't or don't know how to solve the differential equation? There are several differential equations, even to the present day, that are very difficult to solve and don't have analytical solutions to represent those particular curves. So do we still have a tool to help us get some sense of the solutions for that differential equation, even though we don't know the name of the function that represents them? The answer is yes, and the answer is always yes. So the tool that can give you some sense of the shape and behavior of the solutions is what we refer to as slope fields. Slope fields. So let me just illustrate slope fields with a very basic example. Let's look at the differential equation y prime is equal to 1 over x. So we probably should know how to solve this differential equation. This differential equation has the solution y is equal to the natural log of the absolute value of x plus some constant c. But let's pretend that this equation was very, very difficult and you have no idea what this differential equation exactly looks like. So what does an equation tell us if it's a differential equation? Keep in mind, y prime is just another way of saying dy over dx. It's an infinitesimal change in y divided by an infinitesimal change in x, which can be viewed as the slope of a tangent line to a curve at any given point. So what we have here is the slope of y at some point x in the domain of y is equal to 1 over the value of the point for which we're analyzing the slope of y at, right? So we know the slopes of the solution, but we don't know what that solution is. That's in some sense what a differential equation tells us. So if we know the slopes follow the pattern 1 over x, what does that sort of tell us about the original function y? So let's create a little table of values. So let's actually look at a bunch of different x values. So let's look at -10, -5, -1, -0.1, 0, 0.1, 1, 5, and 10. Now I'm actually not going to look at different y values because the right hand side doesn't really change with y, it only changes with x. So when x is equal to 3, the slope is going to be the same at all y values along x is equal to 3. So I'm just going to be looking at the slopes because it's going to be the same across all horizontal values for a chosen value of the domain. So when I plug in -10 for x, what I'm going to have 1 divided by -10. So the slope at x is equal to -10 is going to be something very small, like -0.1. Divide 1 by -5, that's going to give us -0.2. Then we're going to go to -1, -10, and on the opposite side it's going to be symmetric, 10, 1, 0.2, 0.1. And depending on how you look at 1 divided by 0, whether it's from the left or the right, it's going to be minus plus infinity, i.e. the tangent line is going to be a vertical line at that point, at least in some sense. So if we draw a bunch of tangent lines in this space, what do we get? So when x is equal to 0, we're going to have a bunch of vertical lines, right? So i.e. we probably have a vertical asymptote at x is equal to 0. That gives us some idea. When x is really close to 0 on the left and right, we have really steep negative slopes on the left-hand side. So really steep negative slopes on the left-hand side, and really steep positive slopes on the right-hand side. And as we get farther away from 0, the slopes start to shallow out. On the right-hand side, it's still positive. On the left-hand side, it's still negative, but it's not as negative as it used to be. And then notice that the slopes are getting close to 0. So almost horizontal, practically horizontal, but not really horizontal, but I'm sort of stretching my lines out so they sort of have that shape that they're supposed to be hinting at, right? So this gives you what we call the slope field for this differential equation. In some sense, what you have is a bunch of flow lines, if this is, for example, time dependent or something like that. So if you were to sort of connect these lines with each other, what you would have is a bunch of solutions that sort of fit these lines pretty much perfectly, right? So if you can sort of visualize, what we have here is a bunch of these particular curves, right? So you're like, okay, well, those are the particular solutions that you would have. So if I were to pick, for example, an initial condition, for example, this one, then I would be looking for that particular solution to that differential equation. And if it's the absolute value of x, then it probably would be the opposite side as well, right? So you would have solutions that pretty look like that. My drawings are pretty ugly, but hopefully you get the picture. So you might not know exactly what that function is. If you know the graph of the natural log of absolute value of x, you actually should know that that is what the solution actually looks like. But generally speaking, we do not know the analytical representation, but this graph will tell you the behavior at all points of the domain. So slope fields definitely are a very powerful tool, but you probably would have to use software to get a more accurate representation, especially if the differential equation is very complex, and MATLAB is usually a good go-to for such analysis. But those are the main things that you definitely should know when diving into a field of differential equations. All your classifications, how to solve separable equations, and having slope fields to analyze differential equations in case you don't know the method to solve it. Hope you enjoyed this video, and I'll see you in the next video of differential equations. Take care.